All right, we've talked about force and velocity. We've seen some negative values creep in, and I mentioned direction, right? And this is important. It is important when you solve problems, but fundamentally it's important that you understand what happens and why direction comes in and what exactly we mean with certain quantities, certain things we measure having direction, and some we don't. I'll talk here about two things that you probably need to understand, right? And I'll write them down here. We'll start with the first term, a vector. A vector is something, any quantity where we have direction, but we also have magnitude, obviously, right? So, an example, velocity of 100 kilometers per hour. It has magnitude. That 100 is its magnitude. It has direction. You're going left to right, and if you were going left to right and you going the other way, it'd be negative. But that is what a vector is. It has magnitude and direction, right? Relative to a scalar. So here I'd say magnitude and direction. A scalar only has magnitude. So velocity of 100 kilometers an hour. Hey, but the speed cams in the street, we all talk about speed. Well, because speed has magnitude but no direction. That's probably why speed cams don't work in opposite directions. You could, if you drove back against it, they wouldn't know what to do. They only go in one direction. They're not interested in your direction. It's only in the value of the magnitude. That's why I call it speed. So if velocity is a vector, speed, spelling of speed. Speed is a scalar. All right. Now, let's try to map the other variables that we know and that we've studied so far into these two buckets and see where we go, right? What about mass? The amount of matter, its magnitude. Does it have direction? Unlikely. Not in classical mechanics, not in classical physics. There are some cases where, in Einsteinian physics, you'll see negative values, but that's for antimatter and all of that. But for practical purposes, no. Mass is scalar. All right. We looked at time. Does time have magnitude? Yes. An hour, a day, whatever. Does it have direction? In our universe, again, classical mechanics, classical physics, I'm really nervous because I also love Einsteinian physics, and when I read about those and I see negative values in time and mass, it kind of makes me nervous. But classical physics, time only moves in one direction. So when you solve a problem and you try to get time, and if you got a negative value, something's off. You probably want to rework it. Previous video, if you remember when I did square root, I didn't have a plus or minus. The time is a scalar. Okay, what else did we have? Acceleration, well, velocity is, acceleration is also a vector. You might look at a negative value of acceleration and say, well, that's just numerically negative, which didn't really happen didn't seem to be conveying the message of direction. It's just numerically negative. Well, think about it this way. If you've got a high initial velocity and you get to rest or you drop your velocity, right? The acceleration equation will give you a negative value for acceleration, right? But think about it this way. If this is the direction I was moving, high value of initial velocity, low value final velocity. Therefore, acceleration negative, it's deceleration. But think of it this way, it's almost as if something was acting in the opposite direction that slowed you down, right? So acceleration, in a sense, also has direction, right? And that's where that negative value comes, and therefore it is a vector. Okay, if acceleration is, velocity is, we could not miss force. Forces. What about momentum then? Momentum also had direction. That's why when we did changes in momentum, but that we capture in force because a change in momentum is force, so we did capture that. But if you wanted to make a note, yes, if you've got velocity that's a vector, you multiply that with a scalar quantity, nothing happened, you just change the magnitude of the components of that vector. So momentum would be, right? I'm not going to write that down because I have captured force. All right, now for that one big thing, distance or displacement. Ooh, this is interesting. Again, when I started in the basic section, I went over displacement and distance, I explained that, and I also cautioned that some curricula and some examination questions, depending on the syllabus you're studying, sometimes use displacement and distance interchangeably. Pay attention. That is going to become a little more clear here. If an object was displaced, so I'm holding it here, right, and it's there, you could argue that, hey, he's moved it from your perspective, left to right. My perspective, it's moving right to left, or the opposite direction, which means that displacement, the object is displaced, has direction. But the distance I travel is a measure of how much that displacement was. So distance by itself is a measure of value. It's got magnitude, but it's displacement that has the direction, right? So displacement, and this is important, and that's why I covered this in basics. Displacement is a vector because it has magnitude and direction. Distance is a scalar quantity. Now for some of you who are thinking ahead, you might go like, wait a minute, if you said distance and time was velocity, how did you take two scalar quantities and come up with velocity, which is a vector? Well, in reality, and that's why we went back to that original video, it's displacement over time that gives you velocity. We use distance because that term is often interchangeably used in many textbooks. But in reality, displacement in time gives you velocity. So you might have moved, if you look at that very first video one that I had, I've moved 30 centimeters and then I've come back 10. It's overall, my velocity is the displacement divided by the time lapsed. That defines my velocity, right? So understand this, important. I'm not sure at what level you'd have an exam that challenges you with this kind of a trick question, but this is a conceptual question, and I have seen even university level students struggle with this. So remember this is important. Okay, we've captured most of the key variables that we've talked about. Quick question here. I'm not going to give you the answer. If mass is a scalar, is weight a scalar too? I'll let you decide. Okay, all right, we've done this. Now I'm going to extend this concept of vector and scalar, tie it back to what we covered in the previous few videos, right? We saw force get a negative value. We've seen velocity get a negative value. We want to just make sure we understand the notations of these, right? And then we'll talk a little bit about their manipulation and things like that. So when I come into a vector, I'm always going to do, if it's velocity, I'm going to try and write it like this, just to denote that as a vector. Okay, a little arrow, in this case, the arrow goes left to right as we look at the board, right? And that's how I denote it. It's important to get that fundamental idea within you, right? So that you know that when you calculate something, you're setting a direction in the problem, right? And then if you get a positive value for this, you could just say, oh, that was my velocity in that direction, and if I get a negative value to this, you'd still say you're not gonna do that, you're not gonna do that. No, you're still gonna write that, but you're gonna get a negative value, which will tell you that, oh, the object moved in the opposite direction. So this is very important when you do collision problems, right? Classic problems, way up to the further mechanics curriculum, right from, let's say, high school or even before, where they'll give you an object, they give you another object, straight line collision, and they'll ask you to say, okay, what happened to object A and object B, and what happens to object A? And if you try to do the momentum calculation, you get a negative value for V, which simply means object A has moved back. So setting direction is important, and that is kind of why we have vectors denoted with this, right? So I want you to remember that when it comes to vectors, an important idea. So that's the notation. What I also want to denote here is the idea of an absolute value. So that's a vector. And if I take the absolute value, sometimes also written as so I'm setting you up with all of this because there'll be a lot of math that comes in when we start. We'll also go into the math of manipulating vectors, but I'm setting you up with this just so you know what vectors are. They've got direction. This is how we denote them. Convention of mathematics. And then as we go on, we'll manipulate them. We'll see what happens. We'll probably, I'm going to try and take this with the help of some real life examples so you understand why even bother about direction. But we'll get there. We'll get there. Okay, so absolute value. And if I have a vector, and I basically take the absolute value of that vector, what does it mean? It meant that if my velocity came back with a negative value here, and I said, oh, after collision, my velocity is now negative 3 meters per second, and now I go in and take its absolute value, what am I doing? I'm simply taking the negative out, and I'm coming down to 3 meters per second. What have I reduced this down to a scalar called speed? So an absolute value for vector typically will give you a scalar quantity, right? And that's really what we do. Why do we do this? We do it sometimes when we do vector multiplication, and that is something we'll get to, and we'll try and illustrate why we would do a vector multiplication. And before we get there, we'll do an example. We'll try and learn the math behind this using some physics and hopefully tied to real world, but these are just ideas I want you to keep in mind. Okay, what else do we want to do with vectors? Here's another part that I think you should remember about vectors. Because they have direction, well, maybe this is also the time when we change this, or rather up the ante a little bit. So far, everything we've done is in one line. We've talked about objects colliding that way. We've talked about straight vertical drop. It's just one line. You could argue there wasn't really need for direction, just positive and negative would suffice. But that's not the real world. And I'll start, or rather I'll throw an example at you, and then from there we'll probably come back into a continuation of this on vectors. But the example I'm going to throw at you is if I have a street, and if I have a street here, or a road, or whatever, and on this is a block of, let's say, a pallet of boxes, and again, I'm moving stuff, so this is a real example for me, right? Forget about having smooth wheels, and I'll just assume it's a nice, clean, smooth surface, no friction of any sort, and I have this big pallet with a lot of boxes in there, right? There are all my stuff packed up and all of that. Okay, and I'm gonna have to pull, let's just say pull this. Um, so that is me. Not as large as me, but yeah, that is me. I bought me a string, which I'm gonna tie here, and then hold it over my shoulder. And I'm gonna walk. I'm gonna try to pull this. This is at rest, right? It's at rest. It's got a mass of m. Its initial velocity is 0. I'm gonna have to pull this, which means some force that's gonna have to come from me via the string. And I'm gonna want it to move along the, I'm not gonna obviously try and make it float in the air as a string, it's gonna fall, but I'm gonna expect it to move along this. I'm exerting this. If I met you, and you told me, hey, why are you doing that? Why are you taking it over your shoulder? Why don't you just tie it to your waist? And it's gonna be a lot easier. That's gonna be a lot easier. And you're a student of physics, you know mathematics. Well, okay, but guess what happened? I want this object to move in this direction, and my force is applied in this direction. You're asking me to apply it in this direction. Oh my goodness. So you can, I hope you can appreciate why I'm now, we've talked about direction, vectors, forces vector, we've talked about that, but I hope you can appreciate where I'm tying this to in real life. I wanted to move there, right? Yeah. I wanted to move there. I hope you can appreciate why the idea of direction, why just not here simple movements. But in real life, we have several directions, right? And for most of this course, we'll do with the 2 dimensions. So it's that one dimension here, one here, which gives us a series of directions. But that is the thought I want to leave you with. We're going to come back in the next video. We're going to look at vectors a little more closely, and we're going to see how we map them out in 2 directions, in 2 dimensions, and what we can do with them. But I'll leave you with this idea. Is it really true? Think about it. Maybe you already know the answer. But see you in the next video.